Yeah, I see it.
Apparently starting to get some heat on Twitter and on the meetup side because some people are downstairs and we reach capacity. So I think this place, rightfully so, is enforcing the limits more strictly now. So I would encourage people to show up on time like you guys did. Unfortunately, there's absolutely no way we can predict exactly how many people are going to show up or not show up in an event. Sometimes 50% of people actually show up. Sometimes it's more than that. So again, I think the only way is for people to show up on the audio side. With apologies for the people who are downstairs. On that note.
Cool. Thank you very much. My name is Michael Schmidt. I'm the CEO of Newtonian. And I'm here to tell you guys all about the research I was doing and how this sort of spurred a company on the edge of artificial intelligence and where we're going to be applying that to business intelligence. Right? So back when I was in grad school, I was working on this problem. I wanted to help scientists get to a discovery faster. So I worked a lot on algorithms, different techniques to try to leverage data in new and interesting ways. And it turns out it's a really hard problem to help scientists come up with a new hypothesis on something that works, right? I think we spend most of our time as scientists, analysts, searching around for patterns, but it's really, really difficult to find a meaningful, significant pattern. Something that's descriptive of what's going on, where we can kind of cut through the visualizations and the analytics and get to what's at the heart, really the physics involved behind the system generating the data that we collect. So I remember banging my head against the wall for a couple of years in grad school trying to make this stuff work. And eventually we had a breakthrough and we got tons of cool publicity and press out of it. And the phrase that they sort of coined or latched on to the research that we were doing was the robotic scientist, right? So I love these pictures. So here's a few of the graphics that the media has come up with to try to describe what a robotic scientist is. So I think this one here is in Nature News, a robotic head that's analyzing itself. This one I think was either from Wired or New Scientist. It's a robot in a lab coat. How much more robot scientist can you get? And actually, if you go to Google and you search for robot scientist, you get this cool picture of a light bulb with a clipboard, sort of the epitome of a robot scientist. But what we really mean, what a robot scientist really is this, right? It's a software that's communicating the patterns back to you. And behind the scenes are servers that are crunching the numbers, telling you what's significant, what's important, how things work, right? And when I got to thinking about what's so important about a robotic scientist is that when you have a robot scientist, just like in science, you can get actionable understanding, not just predictive understanding or reactionary, but actually strategic, actionable understanding. If you understand, you appreciate how things work, you can act in ways you haven't been able to do before, right? So that's what we're trying to achieve here. And this is the result. So we have a software out today. It's desktop software. It runs locally in your own machine, or it can go out into the cloud, into Amazon's cloud at a click of a button. And it's been enormously popular. Like, it blew me away that there's this much interest in this stuff, right? So we've been installed in I think we're up to about 50,000 systems now in about 90 countries. And we're growing by about 1,500 new users, new trials of the software per month. And we've been, really exciting for me, coming from, right out of research and science, is seeing all the publications that are coming off where they're citing us in the results. So up to 80,000 independent, peer-reviewed publications where we're directly citing the results of this cutting-edge research. Really, really cool stuff. And it's everything from, characterizing how galaxies form in the universe to early signs of macular degeneration in life science to understanding how a business works. And also, we had just a massive amount of computing that's now being done on our platform, right? So people are testing out quintillions of formulas, thousands of trillions of formulas against their data using our software. Like, just since the talk started, there's probably been over 1 billion different formulas tested. And we recently got a bug report where someone wrote in and said, hey, every time I run your software, my laptop gets really hot and it makes noise, right? So that's really the software kicking in. It's using a lot of CPU power. I really don't want to imagine what the impact all the hot laps are out there from running the software. And we're also growing a community around this stuff. So we're actually up to about 1,000 community members that are all using and collaborating with this software on how to find these types of physical patterns, relationships in their data. So I want to step back for a little bit. So this is me back in grad school. And this is sort of the moment right before we had our publication on how this stuff came out. And what we were trying to create was this camera setup that could watch. This is actually called a double pendulum. It's this sort of weird arm on an arm. It's a pendulum connected to another pendulum. And it swings around. The idea was to have these cameras watch this thing, collect data on it. It would send it down to the basement. You'd think about the data. And it would come back with the characteristic equation. How does this thing actually work? The same thing that if you put a scientist or a grad student or an army of PhDs to try to figure out how does this thing work? How is it put together? All you have is the data. Tell me the most elegant, the most beautiful results. That's what we're trying to create. That's what we're able to achieve. It's very, very cool. So we had our breakthrough moment. We got published in Science, cool stuff. And we're able to go from this chaotic system to the chaotic data to a conserved quantity, the characteristic equation of the system, which describes beautifully how everything in that system works, right? It describes how things are connected. It tells you what's sensitive to other things. It tells you how to manipulate the system. And actually tells you a very deep fundamental truth about a double pendulum. Does anyone know a conserved quantity of a double pendulum? Do you guys think back to your physics lessons and maybe anyone think of what's conserved in the system? Approximately angular momentum. So there's actually gravity, so like the velocities will change and slow down. That's actually one of the things that we found. So actually the next best pattern, next best physical relationship is angular momentum, because our data we collected is at high speed. There's another concept, which is good, which is the one I'm showing right here. If anyone is a physicist, you might guess. So one thing is energy conservation. So this is actually detecting that, hey, this thing obeys energy conservation in the universe when it swings around. So that's cool and all. So I want you to sort of think like a robot scientist for a moment, right? So imagine you're presented with this data set, right? So imagine we have X on the X-axis here, Y on the Y-axis. What is the formula that captures what's going on here? Does anyone have a guess? Think about it for a second. So I once gave this talk to a math group at Cornell University, and someone got it like that. It made me look really bad. Does anyone think about what an answer to this might be? Someone take a guess, because you might be right. Sine times something. Okay, that's good. No, not the sigmoid. Not the sigmoid. All right, let me show you what the answer is. But you can imagine, if you were a robotic scientist or you had an algorithm to try to capture this stuff, how would you go about doing it? One way is to start trying things, right, and see how well it works. Let's just try to fit the data. Just do curve fitting, but let's do it in a nonlinear sense to try to find something simple first before we get into something complex, right? So maybe something simple here. You guess the sine. We'll try that one first. That's great, right? You can imagine evolving this and getting better and better and better, trying to tweak this over and over again, right? Until we sort of latch on to, hey, we've captured a ton of the variation in this data set with this really simple nonlinear equation. This is something very interesting that it's able to capture all the dynamics so simply with this limited set of building blocks and this very short expression, right? So what's actually going on behind the scenes is we're searching the space of nonlinear equations where we represent these as a binary tree in memory, where every operation is, every node is an operation, like a mathematical operation. So this one breaks down into multiply and then a subtraction and the addition on the right. And we have a really smart way, intelligent way of generating a candidate hypothesis, generating a useful, potentially interesting nonlinear expression. And the way the algorithm really works is it's a lot like how science progresses, in the sense that you might imagine there's physicist A, and he's got his theory of gravity, and you have physicist B, he's got a different theory of gravity. So in the real world, if they go out and they design a new experiment to see who was right and who was wrong. But what's so cool today is we have enough data, we don't have to design and collect new experiments. We just need a smart way of picking that data point to see who was right and who was wrong. So we have a really efficient way of actually generating and sampling these expressions and actually testing out which ones are right until we converge onto a minimal structure. So one interesting thing is it's actually really, really easy to fit data. It's quite boring. You have a really large, complex model. Maybe it's a neural network. Maybe it's a random forest, or maybe it's just a really large polynomial. So you can have a really complex formula way out here that captures all the dynamics. It fits it almost perfectly. Like that's a solved problem. We've been doing that in machine learning for forever, right? We can fit data really, really well. On the other extreme, we can also, have really simple models, right? They have high error, so you can imagine this is actually a linear model, right? A single, simple, one variable linear model. Doesn't really fit the data very well, but it's a start. It's got high error. But what's really cool is what's in between, right? So not something that's just accurate, but also simple at the same time. In fact, if you do this exhaustive search over the space of nonlinear expressions, what you actually get is this frontier of potential explanations. So different levels of approximation, and all the way out to the most accurate statistical model you could possibly have if you want to put enough computational resources into it. So this is what we calculate in the end, are this list of the best potential models, nonlinear expressions, physics to describe your system. And we leave it up to you. So if you want to work with the simplest possible approximation to the system, you can pick that one. If you want to be somewhere in the middle where you get the maximum insight, simplest model that captures like 99% of the variance, or if you want to go all the way out to the most statistically accurate complex expression, you can calculate that as well. So that's the cool thing about this. So I got up to everything I've described so far. We've been helping scientists that want to understand how the physics of their data works, what's going on behind the scenes. But you might have noticed there's almost no laws of physics in business, right? And why is that, right? It's hard to do. It takes extreme expertise to be able to do this sort of stuff, right? So I saw a real potential business opportunity here and started thinking about forming a company around this stuff. But what would be sort of the founding principles of that company, right? So the number one for us is understanding. There's something critical about being able to understand the things that are going on in your data. Finding things you did not know existed, and then actually being able to understand and appreciate how they work so you can take action on them. And the cool thing is when you have understanding, it empowers you to take action, right? So it gives you the strategic knowledge rather than the reactionary predictive knowledge. You can get to the action very, very quickly. And third, we want to be able to unite artificial intelligence with business intelligence. Right? So there's a lot of software out there now that have, if you already know what you're looking for, you can have these huge scalable systems that can query it and find the, calculate the results for you over and over and over again. But if you don't know what's important, if you don't know what your KPIs are, what's actually driving something new or something that's changing your business, that's where it gets really, really interesting, where we can find these things and present them to you. So, where is this where has this gone in sort of the past year? So one of the things I've been blown away by is, just the raw interest in this stuff. So just over the past year, we've spiked it over, 20,000 new installations of the software, new users of the software, and people are just using it more and more and more. So we've seen a ton of computational effort being pulled into this, calculate these sort of results, right? For some reason, there's a lot of interest in this stuff. And we've seen a dramatic increase in our forum users. And not only are we getting more users, but we're also getting more use of the product by those users, right? So more time spent in the software per user. So people are using it more and more and more, which gets exciting. And, we've been putting out a lot of new content to help support this community and these users, everything from case studies to blogs and videos, to product documentation, that sort of stuff. And this is all software that you can download today. So a lot of this part of the business is trying to figure out why has there been this sort of demand for it? What is the real opportunity here? So, I've thought about this for a long time. One way you can sort of break it down is, if you look at the past 20 years of machine learning research, statistics, that sort of thing, there's been really heavy focus on being able to predict, build the most complex, statistically accurate model you possibly can. Right? We've gone really, really far. We've gotten incredibly good at being able to predict and model, fit the data, right? On the other spectrum, we have these data visualization, analytics, that have been helping people gain insights that they've never been able to gain before, right? But where you really want to be is up on this right-hand corner here, right? So here we're talking about an analytical model, which is not only the insight and the predictive power, but a true understanding of what's driving that prediction. So predictions with explanations, and that's where you want to get to. And you think about it, as data scientists, I think you could spend your whole career just trying to cross this chasm, get up to there. We're trying to make that really, really fast, and that's where all our investments are as a company. That's where we want to get to. But I'm really jealous of the data visualization guys, so they have beautiful pictures, and all we have are equations, but we're working on that. Don't worry about it. So I'd like to have a quick demo here. So I have a video I was going to run just to kind of show you guys what this looks like. Can you guys see this? Great. So this is our software, Eureka. You can download it. We've got free versions of everything that we have. If you're academia, you can use it for free, for all your research, and I encourage you guys to do that. Really easy to just download and run. So we're on Windows, Mac, and Linux, whatever you want to do. And the idea is, one of the first challenges is just getting data into a system like this, right? So you spend all your time just getting data into it. So we have just a native spreadsheet format. If you can get your data into a spreadsheet, you can get it into our desktop product as is today. All we need are columns of variables. Give us tons of columns of variables. We'll tell you how they relate to each other in the simplest, most meaningful way. Right? So in this example, I'm just going to try to skip through it here. So this is actually data from a double pendulum, which I was describing before. And here, every column is a variable. So we've got things like time. We've got measurements of velocities and positions. And we can also put in things that maybe aren't related, right? Like maybe we think they're related, but maybe they're not. We could have currencies, categories, Boolean data sets, text. Like this is actually data from our user forum, things like that. So we can support all these different types of data. It automatically breaks them into numerical components and helps you analyze them, right? So in Eureka, you work from left to right. So you can do everything from filling in missing variables to smoothing the data to really simple, basic things you'd always want to do to prepare the data. And then all you have to do is set up a target expression. So here's our equivalent of a Google search text box where you say, I want to understand blank. I want to understand this, right? So here we can let you enter in an arbitrary expression. This is actually, a pretty powerful thing if you're, able to grasp a little bit of math to do some really complex optimizations. And then you go to start the search, and here's where it can either run locally on your laptop, or if you've enabled a cloud, you have an Amazon EC2 account, you can automatically distribute it across, hundreds of cores if you want. Whatever you need to speed up this analysis. So I think for this data set, it takes a few seconds here to kind of collapse onto the best results. So in the results screen, we can see the results coming in live. We start with the simplest approximations to a double pendulum until we converge onto, an optimal result. And what's cool about this is it's a massively parallel algorithm. So as fast as you need it to be with enough computational effort. So in this case, we converge onto another characteristic equation of a double pendulum. This is modeling, the force of gravity on the second arm, and here's the relationship, from that. And what's cool about it is it's picked up things like the dependency on the velocity and the relative positions of the two arms of the pendulum. You can actually see there's a coefficient in here which is 9.8. If you guys remember physics at all, that's the coefficient of gravity in this sense. But we didn't vary gravity, we didn't give it that, so it had to reduce that acceleration from gravity. And then you can do all kinds of cool things, like you can look at the results and copy and paste them into anything, Excel, MATLAB, Mathematica, whether SPSS, whatever software you use. So a lot of our customers now and a lot of our users use this as the starting point to find how things work. And then they do all the complex analysis they would be able to do if they understood all the physics of the system after that. So another cool thing is we have a ton of reports on and explanations into not just giving you the math, but actually describing it to you. What does all this stuff mean? In fact, that's where we're going long term, is not just computing these results, but also translating them back to you in a useful way. So what's cool here is we gave it a ton of variables, but it only picked up on the relevant ones. So it picked up on what's useful and what's not, right? Automatically, directly from the data. So I want to get back to the demo here. So I need to speed up. Nope, that is not what I want. Thank you very much. The mouse is moving on its own. Cool. All right, so let me tell you about a few use cases really, really quickly because I only have a couple minutes left here. So one of our coolest use cases is with Dow Chemical, and this is a case where they're trying to optimize production of something like a glue, like how sticky is a glue, or different properties like this. And it turns out they can make these things in a test tube almost perfectly. But when they want to make them at scale in production, there's a huge challenge of just being able to scale up what they do and achieve the same properties, the same characteristics. It's a black art making these things work because there's so many different combinations of the chemistry and the production process that go into this thing. No one truly understands the physics behind these things. So I have to go on site, and there's actually a lone guru that kind of knows which levers in this manufacturing plant they should be turning, which dials they should be adjusting to achieve what they want. But he just retired last year, and he's a cool guy, and it's a shame. But what we allowed them to do is take that same process data and get the same level of guidance in terms of optimizing for something like their yield or their literally a stickiness of a glue or durability of a paint or the size of a resin, things like that. One of our other biggest customers is the Air Force, and this is a case where they do a ton of work trying to detect when failures happen. And there's a lot of things that go into failures and actually being able to detect when cracks form, microscopic cracks form in the material. We actually applied this technology to help them do that almost an order of magnitude, sooner than they've ever been able to do it before. And this is really awesome. Like they insisted we get a patent on this particular application, all this other stuff. And now they're scaling out to all their sort of inspection, all of their engines and things like this to save a ton of money. I don't know how much they save from not having to replace these things as often. And then we also seen, surprisingly enough, really interesting use cases in retail. So, another recent customer of ours just wants to understand what are the drivers of sales, right? This is something that a lot of people probably spend their careers trying to do. What if you let your data give you some direction on, a compass to understanding what's actually driving sales of individual products, individual stores? Why is one store succeeding, another one not succeeding? We can throw in tons and tons of data, right? All kinds of things like demographics, the historical data. How do we actually know what's actually driving that without spending a ton of effort in there? There's clearly some physics, right? So we can throw all that data in there and crunch the numbers and see what that relationship is. What is the physics of sales of this particular product? It's a cool problem. And we can do it at a massive scale now. And then really cool for me is to see all the publications that are coming out of applying this in research and technology, how people are leveraging it on academic data sets to life science to all kinds of wild stuff. And this is all on our website. If you guys are curious, it's pretty neat to see. So, real briefly, we've got Eureka Desktop, Eureka for Excel. Like you can just do this in Excel. If you're a more advanced user, download the desktop product that I just showed you. And where we're really going with this is making this more consumer friendly for a business user, a business analyst, and this is the enterprise product. And ask me more about that later. It's a early access at this point only. So I really could encourage you guys to go out there, try this stuff. We've got free versions of everything. Really easy to get started. Plugs right into Amazon if you ever need it. And you can start finding these sort of relationships immediately. Thank you very much. Thank you.
But you guys didn't realize you'd be back to physics class tonight, huh? There was one question here. We have time for one quick one, and then Michael, you're going to be around after this?
Yeah, absolutely.
Okay, terrific. Or you here? Okay, sorry. Next time.
Yeah, hi, Ryan. I work at LogicWorks. I'm wondering, is there a relationship between the randomness of the signal that you're processing and the outcome of the software? In other words, how accurate it is? Could it handle deriving like the gravitational constant versus the randomness of, say, a heart rate signal the same way?
So really, it depends on how you frame the problem. So you can model things like distributions, CDFs, PDFs, that sort of thing. You just have to constrain the problem a little bit differently than what I demonstrated. Literally anything you could write down as a simple expression you can do in the desktop software today. Also to your point of, if you give, one of the experiments we do is we throw in random data, right? If you give junk in, what do you get out? Right? That's usually the first question I normally get. And in that case, we can tell you, the best you can do with the data you have is predict the mean, right? And sometimes that's a disappointing answer, but it's a good one to have. So we can actually tell you, if you don't have enough information, what's the best you can possibly do with a nonlinear model. And I'll be around. Thank you very much again, and please just grab me afterward.
Thank you very much.